Okay, we are back and we are better than ever. Today we are talking about the standard normal distribution, or the Z distribution. What is the difference between this and what we learned about the normal distribution before? Well, in some cases we need to standardize our data. For example, if we're comparing results from two or more different distributions. What in the world does that mean? Well, let's say we had a student who had a score in a history test and in a math test, and we wanted to know how that student performed compared with the rest of her class. In which class did she perform better, math or history, compared to the rest of her class? Well, if we just did plain old normal distributions, we would have different standard deviations, and we couldn't compare the two. But if we standardize all our scores, all of our data, then we can indeed do that and see how the student compared to her peers, and how she did better in either of the two courses. And we do that by standardizing each piece of data using this formula and getting the z-score. We take the piece of data, we subtract the mean of the data and divide by the standard deviation, and that formula is right here on your formula sheet. Seems confusing now, but by the time we're done you'll see. It's really quite simple. The reason that we do that is if we take each piece of data, every single piece of data in a data set, and we standardize it, and then we calculate the mean and standard deviation, it turns out that the mean of that data will be 0 and the standard deviation is 1. Okay, so that makes all of the data have the same mean, 0, and the same standard deviation, 1. Both very, very, very nice. And we call this a standard normal distribution, not just a normal distribution. And the only difference is that we know that the mean is 0 and the standard deviation is 1. Okay. This is just showing that if the mean is 0, we're going to have data to the left of the curve and data to the right of the curve. And we are going to be able to use symmetry to find out some of our values. And since the data is standardized and every mean is the mean of every data set is 0 and the standard deviation is 1, we have tables that we can use, which you'll have to do on paper 1. This table is in your formula packet. There's more to it than this. I've just cut out and pasted the parts that we need. Now, these scores have already been standardized for us. In other words, the formula has already been used to get these values. So, and that they tell us that right here. If z is a standard normal variable, already is, find without using technology the probability that z is less than or equal to 1.5. Very simple. 1.5 is here, right here. It's 1.50 right here, so we just go down our little row right here, and we get 0.933. So about 0.933 is the probability. You could also write that as 93.3%, but this is just fine. Remember, 3 sig figs on everything IB. Okay. Now, this table always gives you the area to the left of the data value, the area under the curve to the left of the data value. So if we were asking what's the probability that z was greater than this, well, this would not be our answer, but we could use it to get our answer because of the symmetry. And we'll see that in example B. Here we're being asked, what's the probability that z is greater than 0.84. Okay. Well, remember, the area under this curve, the standard curve, is equal to 1. So if I take 1 minus this area, I get this area. Okay. Or if I take 1 minus this area, I get the area that I'm looking for. And remember what I told you. This table gives us the area to the left of the data point. So if we want the area to the right of the data point, we have to subtract what we find in the table for this value from 1. Okay, so the probability that z is greater than 0.84 is 1 minus, okay, so here's 0.8 and 0.84. We go out to the 0.04. We go down there and straight across there. So it's 1 minus 0.7995. And that is equal to about 0.200 to 3 significant figs. So I should say this. So our answer is about 0.200 or about 20%. Okay. Well, what about our calculator? Well, let's do this one real quick. Let's go back. Our answer was 0.933. It's very simple on our calculator. Probability that z is less than or equal to 1.5. Menu, probability, distributions, and this is a cumulative normal distribution. There isn't a special button. The lower bound is 0. Let's go back again and take a look at our curve. See, we go, or I'm sorry, not 0, negative infinity all the way back here. I said 0, negative infinity. And our upper bound is going to be 1.5. Okay, so it's very simple, very easy. So upper bound 1.5. And here's why we don't have to have a special button. The mean is 0, standard deviation is 1. Bam, there's our 0.933. Okay, and so then we could also do our second example by just doing 1 minus the probability of 0.84. Okay, so let's do that. Okay, normal CDF, probability. Well, actually, we don't have to do that, right? Distributions, normal. With a calculator, our lower bound for that one is 0.84, and our upper bound is, let's see, 1 EE to the 99th. We hit OK, and we get our 0.2000. I was having trouble remembering if this was 1 or 10. Sorry about the pause. Okay, so we don't have to do the 1 minus thing if we have our calculator, because we can do our lower bound and our upper bound. This is to positive infinity. Okay. I'm going to stop it there because C is a little bit involved, and we'll just take a break here and we'll do the next video in a sec. See you in a minute.